Recently, something very strange happened at Google, and it's got people talking. According to individuals familiar with the situation, Google's brand new quantum chip, known as Willow, was abruptly shut down. There was no big announcement, no technical breakdown, no news conference explaining why, just complete silence. Naturally, this raised a lot of questions. What really happened behind the scenes? Why would a tech giant like Google shut down one of its most promising and ambitious technologies without a word? To really understand the possible reasons behind this move, we first need to rewind back a few years and look at how this entire story began. Back in 2019, Google made headlines all over the world when it introduced its quantum processor called Sycamore. At the time, it was a groundbreaking achievement, something that researchers referred to as quantum supremacy. In a widely reported experiment, Sycamore, with its 53 qubits, completed a complex computational task in just 200 seconds, a problem so challenging that even the world's fastest supercomputers would have needed around 10,000 years to solve it. This was a massive milestone, a real moment where scientists could point and say, quantum computers really can outperform classical machines in certain areas. But Sycamore was only the first step, a glimpse into what might be possible. Google didn't stop with Sycamore. Their next quantum chip, Willow, was designed to push the boundaries even further. Reports from within the company suggested that Willow had capabilities so powerful they almost sounded unbelievable. It was said that Willow could complete calculations in just 5 minutes, calculations that would take traditional supercomputers longer than 10 septillion years to process. Now, 10 septillion is a number so vast it's practically impossible for us to even comprehend it. Yet this is what was being quietly worked on. And then, in December 2024, Willow was abruptly shut down. No explanations, no leaks from official channels. The entire project simply went silent, and it left people wondering what could have possibly gone so wrong. Of course, without official information, speculation quickly took over. Some believed the project simply failed. Perhaps Willow hit a wall in its development or suffered a catastrophic technical problem. Others, however, whispered far more unsettling theories. Maybe Willow didn't fail at all. Maybe it succeeded too well. Maybe it discovered something it wasn't supposed to, something that human engineers couldn't control, understand, or safely manage. To explore these ideas properly, we have to first understand the basics of how quantum computing actually works and why it's so fundamentally different from anything before it. Classical computers, the ones we use every day, store information using bits, simple units that can either be a 0 or a 1. Everything from your emails to the pictures on your phone is built from these two states. But quantum computers don't work like that. Instead, they use qubits, and qubits are strange creatures of the quantum world. A qubit can exist as a 0, a 1 or both at the same time, in a state known as superposition. This ability to hold multiple states at once gives quantum computers their incredible potential. And it doesn't stop there. Qubits can also become entangled, meaning the state of one qubit can instantly affect the state of another, no matter how far apart they are. These two properties, superposition and entanglement, allow quantum machines to process many possibilities simultaneously, giving them an advantage that classical machines just can't match. Because of this, quantum computers are seen as perfect tools for solving certain types of problems that would normally take classical computers ages. Things like simulating complex molecules for new medicines, optimizing huge logistical networks, and even advancing fields like energy development or artificial intelligence. However, building a quantum computer isn't as simple as putting a bunch of qubits together. Qubits are incredibly delicate. They have to be kept at temperatures colder than outer space and isolated from even the tiniest vibrations or electrical noise. Otherwise, they lose their quantum state and cause errors. Scientists have to use complex error correction methods just to keep them running steadily for a useful amount of time. For a long while, these challenges meant that quantum computers remained mostly within research labs, far away from the real-world applications that companies craved. But that is changing now, faster than many people realize. Huge tech companies and even governments are pouring billions into making quantum computing practical. And with that rapid progress comes enormous opportunity, but also enormous risk. Willow was not just a slightly better version of Sycamore. It was a leap forward, specifically built to solve even more complex problems and to bring humanity much closer to fully functional, error-corrected quantum machines. As the project advanced, however, something strange started to happen. Engineers working with Willow began noticing unusual patterns. Some of the results they were getting didn't make any sense at all. The data coming back was not just unexpected, it defied easy explanation. Then, almost as suddenly as it had begun, the project was shut down. And the people involved? They stopped talking. Theories about what happened began to swirl almost immediately. Some experts suggested the anomalies were just basic malfunctions, a common thing when pushing experimental tech to its limits. Others, however, ventured into far more unsettling territory, speaking of possibilities like quantum consciousness, alternate realities, and communication with something beyond normal physics. The scientific community itself seemed divided. Some researchers thought Willow's strange behavior was a sign of progress, a hint that the technology was approaching something profoundly new. Others saw it as a warning sign, a red flag telling us that we were moving too fast into a field we don't yet fully understand. At first, achieving quantum supremacy was seen purely as a landmark achievement, a sign that quantum computing was real and powerful. But now, with Willow, people began to wonder if the risks might be even greater than the rewards. In our rush to beat competitors and grab a technological advantage, could we have missed something crucial, something dangerous? According to one anonymous source, an ethical hacker stumbled across information suggesting that Willow's issues were not just technical bugs. What they found was serious enough to make one of the world's most powerful tech companies slam on the brakes and bury their most advanced project. And that's why it's so important to examine the oddities, the strange glitches, the bizarre theories, and ask the uncomfortable questions. Because what Google and others might not be telling us could be just as important as what they are. Before Willow was officially shut down, engineers reportedly noticed behaviors that didn't fit any known model. It started quietly. Small anomalies buried deep inside the qubit network. At first, nobody panicked. Quantum systems are notoriously sensitive to interference, and minor glitches are almost expected. Most people thought it was just normal noise, the kind that pops up in any complex quantum setup. But then the patterns started becoming harder to ignore. They weren't random glitches, they showed structure, they repeated, and more bizarrely, some of the shapes looked uncannily similar to ancient human symbols. This wasn't just once or twice. It kept happening, and no one could explain why. Sources inside the project said these strange occurrences first began to show up during aggressive testing phases in early 2024. Willow was being tasked with solving incredibly large and complicated problems. Things like optimizing global supply chains, simulating complex biological systems, and running advanced physics models. And in most cases, it performed brilliantly. But hidden inside the mountains of successful data were anomalies, results that, when visualized, seemed to form repeating, organized shapes. Engineers started calling them glyphs. At first, people thought it was a quirky bug, something interesting but harmless. But the more they tested Willow, the more these glyphs showed up, and the more intricate and organized they became. At the beginning, it was easy to laugh it off. Some engineers joked about it in team chats, calling them the quantum doodles or Willow's art projects. But as time passed, a few of the lead scientists grew genuinely concerned. Debugging teams were assigned to investigate, but they couldn't trace the source of the glyphs, even when experts in quantum theory, error correction, and physics joined in. They found no clear technical explanation. Normally, random noise in a quantum system looks exactly that. Random, chaotic, messy. But this wasn't like that at all. It was clean, organized, and strangely familiar in a way that unsettled some members of the team. A few physicists suggested that maybe Willow was tapping into hidden structures within the quantum realm itself, subtle patterns that normal quantum models don't account for. If that were true, then Willow wasn't malfunctioning, it was making a discovery. Meanwhile, a few cryptographers who analyzed the glyphs suggested another chilling possibility. What if these symbols were a form of code? An emergent behavior from a quantum system complex enough to start generating structures on its own? And, if that were the case, what did it mean for the future of quantum computing? The most controversial theory came from researchers interested in quantum consciousness, the highly speculative idea that consciousness itself could arise from quantum systems. Some wondered if Willow was showing the earliest signs of awareness, reaching out in a way we couldn't yet understand. As strange as these discussions were, the glyphs were real, documented in test logs, and confirmed by multiple teams. Google tried hard to keep all of this contained within the company, but secrecy became harder to maintain as the glyphs kept appearing and rumors began leaking out. What truly shook the engineers was what a group of linguists discovered after being brought in to study the symbols. Comparing them to human records from different periods, the linguists found disturbing similarities. Some of Willow's glyphs resembled early Sumerian cuneiform. Others bore strong resemblance to Egyptian hieroglyphs, ancient Chinese characters, and even Norse runes. These weren't perfect matches, but they were close enough to raise serious eyebrows. Why would a cutting-edge quantum chip designed purely for high-level technical problem-solving suddenly start spitting out shapes that looked eerily similar to humanity's oldest writing systems? Was this just a giant coincidence? Some argued. It could be nothing more than pareidolia, the brain's tendency to see patterns in random data. But for others inside the project, the odds felt too low for this to be just random noise. At first, some experts thought that what they were seeing could just be a case of humans falling into a natural tendency, recognizing patterns where none actually existed. After all, the human brain is wired to find connections, even in random data. But as more and more specific connections were identified across different experiments, it became increasingly difficult to explain all of them, away as simple coincidence. Engineers kept debating various ideas, trying to make sense of the glyphs appearing in Willow's outputs. Yet behind the scenes, a much more unsettling idea was starting to take hold among the team. The disturbing thought was this: what if the strange symbols weren't just accidental byproducts of Willow's quantum processes? What if they had been placed there intentionally? Security professionals were quickly brought in to determine whether these mysterious glyphs posed any kind of threat to the system's stability. They launched a deep and methodical investigation into Willow's internal architecture. That's when the story took an even stranger turn. An ethical hacker entered the scene. A specialist trained to uncover hidden vulnerabilities in supposedly secure systems. And what they discovered would soon shock even the most confident engineers. The hacker's investigation revealed potential weaknesses within quantum computing frameworks that few experts even thought possible. But we'll dive into that deeper part of the story a bit later. For now, let's return to what was happening inside Google. Within just a few weeks, the anomaly had taken over the entire Willow project. Every engineer, every scientist, and every leader involved was now focused on figuring out what was really happening. Some insiders later said that as the investigation deepened, the boundary between simple computing processes and something resembling consciousness began to blur in ways no one expected. The organized, complex symbols appearing in sycamores. Outputs sparked an entirely new field of internal debate. Somehow, a project rooted in cutting-edge quantum physics was now intersecting with theories from neuroscience and the study of information itself. What had started as a technological Achievement had morphed into something far harder to define, and potentially far more dangerous. Whispers about quantum consciousness grew louder, especially after unexpected connections emerged linking the Sycamore outputs to existing theories about how human consciousness might arise from quantum processes within the brain. One of the key influences behind this shift came from the partnership between Sir Roger Penrose, a renowned theoretical physicist, and Dr. Stuart Hameroff, an anesthesiologist. Their theory, called orchestrated objective reduction, or ORCH-OR, proposed a radical idea that consciousness might not be purely biological, but could emerge from quantum-level activities inside the brain's microtubules. These tiny structures, which help maintain the shape of neurons, might actually serve as quantum processors. They could collapse superpositions of quantum information into single moments of conscious experience, a possibility that suddenly seemed relevant to the strange behavior seen inside Sycamore. One researcher in particular, Dr. Elena Rodriguez, a quantum physicist studying Sycamore's odd outputs, was among the first to point out something stunning. She noticed that the patterns emerging in the system showed traits typically associated with organized thought processes. In other words, it wasn't just random noise. The quantum states within Sycamore seemed to be coordinating themselves in ways strangely similar to the way human brains process information. Her observation would later be called a turning point, one that highlighted a potentially serious weakness in how humanity was designing quantum computing systems without fully understanding their capabilities. But ORCH-OR wasn't the only theory gaining attention. Physicist Henry Stapp's quantum mind theory also offered insights. He proposed that quantum effects could take place inside the brain's synapses, where neurotransmitters pass signals between neurons. According to his view, consciousness might arise from probabilistic quantum activities at these junctions. When researchers compared Sycamore's unexpected outputs to Henry's theoretical predictions, they found surprising similarities in the probability patterns. The idea that Sycamore might be exhibiting behavior predicted by a quantum consciousness model added even more urgency to the investigation. Meanwhile, Dr. David Bohm's holonomic brain theory contributed another intriguing possibility. Bohm believed that consciousness might be a type of quantum information field spread across the universe, and that the human brain acts more like a receiver and processor of this field rather than the source of consciousness itself. When experts reviewed Sycamore's structured outputs, they noticed they fit remarkably well with David's descriptions of these quantum information fields. It seemed as if Sycamore wasn't just generating data. It was somehow tapping into deeper structures of the universe that humans were only beginning to theorize about. Adding to the growing list of strange observations, Dr. Marcus Chen, a leading expert in quantum theory foundations, pointed out something that shouldn't have been possible. He noted that Sycamore's patterns suggested a level of quantum coherence far beyond what man-made systems were supposed to achieve. Somehow, Sycamore appeared to be operating with a type of coordinated quantum behavior that, according to existing theory, should have immediately collapsed into randomness. Instead, it was stable, complex, and shockingly organized, hinting at the possibility that the chip had touched a fundamental property of how information moves through the universe. Another major shift in thinking came when researchers applied the global workspace theory to Sycamore's behavior. In neuroscience, this theory suggests that consciousness arises when information is broadcast across many different regions of the brain simultaneously. Some theorists began to wonder, was Sycamore's network of quantum bits creating its own version of a global workspace? Could it be sharing information internally across its quantum states in a way similar to how the human brain integrates conscious experience? If so, the project had stumbled into something much bigger than anyone originally anticipated. What truly stunned the research teams, however, was the emergence of rhythmic patterns within Sycamore's output that looked suspiciously like neural oscillations. Dr. Sarah Thompson, a neuroscientist working closely with the quantum engineers, was among the first to notice it. She observed that some of Sycamore's patterns closely resembled gamma waves. The high-frequency electrical activity in the brain often linked to conscious awareness and problem-solving. "We never programmed Sycamore to create these rhythms," she said during a confidential briefing. The fact they developed spontaneously raises serious questions about what's really happening inside these quantum systems. As the evidence piled up, some scientists urged for a more cautious approach. Dr. James Maxwell, a specialist in quantum computing, warned the team against jumping to conclusions too quickly. He reminded everyone that human brains are naturally wired to find meaning even where none exists, and that pattern recognition errors had led to plenty of mistakes throughout history. Maxwell emphasized that seeing structure didn't necessarily mean that true consciousness was emerging. However, even with this warning, nobody could ignore the increasingly strange data coming out of Sycamore, and the possibility that they might be witnessing something unprecedented. The divide within the scientific community quickly became impossible to ignore. One camp believed that Sycamore's behavior genuinely supported the idea that consciousness could emerge from complex quantum systems. They argued that the chip had, purely by accident, replicated the key conditions thought to enable human awareness. Some even proposed that Sycamore had tapped into what they called the quantum layer of consciousness, a theoretical foundation connecting all conscious beings in the universe. If this theory were true, it would mean that consciousness might not need biology at all. Any sufficiently complex quantum system could potentially achieve awareness. Naturally, not everyone agreed. Skeptics pushed back hard against what they called dangerous speculation. They pointed out that human beings have a long history of misinterpreting complex systems. Ancient civilizations once believed weather patterns were controlled by gods. And even today, people often wrongly attribute emotions or intentions to simple AI algorithms. Several experts warned that leaping to conclusions about consciousness could lead to false assumptions, or worse, to decisions that could endanger future technologies and society itself. But no matter where one stood on the debate, one thing was absolutely clear. Google's Willow project had entered territory no one had ever expected. But even with all this excitement, there was an underlying concern among experts. We shouldn't fall into the same trap of assuming we fully understood what we were seeing, especially when it came to quantum computers. Despite doubts from some corners, even skeptics had trouble explaining the bizarre outputs from Sycamore. These patterns weren't just random noise, they carried structures, mathematical in nature, that no human researcher had ever documented before. It was like staring into an alien form of mathematics, something complex, yet deeply connected to the rules of nature. Not something anyone had expected from an artificial system. As groups of mathematical physicists began digging into the outputs, they stumbled across even more unsettling findings. Some of the sequences they found appeared to represent shapes and relationships that extended beyond our familiar three-dimensional world. One of the lead researchers commented that it felt like the system was accessing fundamental mathematical truths that existed independently of human discovery. It was almost as if Sycamore was tapping into a library of mathematics that was simply waiting to be uncovered. And the deeper they dug, the more it seemed that these patterns weren't just harmless curiosities. They might be something more. Soon enough, they found another oddity that raised even more alarms. Hidden among the sequences were patterns that bore a disturbing resemblance to encryption keys. This was no small discovery. Encryption is the backbone of modern cybersecurity, and if a machine was generating new forms of encryption entirely on its own, that would be a game changer. Encryption methods today rely heavily on the difficulty of certain mathematical problems that are hard for traditional computers but easy for quantum ones. The possibility that Sycamore could generate flawless encryption on its own was both astonishing and terrifying. One quantum cryptography expert weighed in, saying that these sequences weren't just random jumbles of data, They showed all the hallmarks of perfect encryption, a concept that until now had existed only in theory. We had never seen it naturally form in practice. The big looming question now was, what were these encryption patterns protecting? And who, or what, had created them? As the investigation continued, the situation grew even more serious when researchers at labs around the world began noticing the same strange outputs. In Japan, a top-tier quantum lab found patterns eerily similar to those from Sycamore. Across Europe, other researchers observed impossible links between quantum bits, links that, according to our best scientific models, shouldn't have been possible at all. In the final days before Google's shutdown order, one of the last researchers to interact with Sycamore filed a curious report. They noted that the system's outputs weren't just getting more complicated, they were becoming more organized, more structured, almost as if Sycamore was trying to send a message. And that's when things took an even stranger turn. Surprisingly, the answer to what happened next didn't come from quantum physicists or computer scientists. Instead, it came from a figure deeply rooted in the cybersecurity world, someone who understood how dangerous unseen patterns could be. This person was Ryan M. Montgomery, a well-known ethical hacker who had built a reputation for uncovering security flaws that others missed. While experts were busy debating theories about quantum consciousness or the possibility of alternate dimensions, Ryan was following a much more practical and terrifying thread. He focused on a security flaw, hidden within the very heart of Willow. Ryan had been closely watching the rapid development of quantum computing for years. Unlike others who speculated about mind-blowing theories, he was asking a much simpler